Hello everyone. So today we'll be solving problems related to week 12 content of control engineering course. And this contains controllability, and observability concept for an LTI system. So basically we are dealing with state space model of an LTI system. So we have this model X dot. Yes, not audible. Okay, just am I audible now? Yes, I think I'm audible now. Fine. So today we'll be solving some questions related to controllability and observability of ITI system. So basically, in last week and this week, we are dealing with this state space representation of system or state space modeling of system, and we are doing analysis for that, and we are also relating how this is related to the earlier model that we have read, which is transfer function. So we have done most of the analysis related to transfer function, the whole root locals and then frequency domain analysis. So the basic motivation was to do a controller design. And for controller design, we are saying that if we are designing a controller, that controller should be such that it should make the system stable. Like the system should be stable, and also there should be some performance that has to be achieved. Now this is related to placement of the poles of the transfer function. So how this is related to the eigenvalues of matrices in this state space form that we saw in last week course, and today also we'll see like how controllability we can say relate this to root locus. All those things we'll do examples and we'll see how we can relate. So we have this form for a state space representation: x dot equal to ax plus bu and y equal to ex plus d. So here x is the state vector. Now suppose this has dimension n, so it is like x1, x2 to xn. This belongs to this Euclidean space R to the power n, and A is this A matrix is there, and we have this B which is relating the this state to the input. So basically from this equation, this is a dynamic equation. We have this x dot. So that means this x dot is dx by dt. So how a state is evolving with time. This is evolution of state with respect to time, and this evolution depends on state and input itself. So previous value of a state and the input which is being applied. And the output of the system is related to a state again and the input. So when this D means if there is no direct feed forward from input to output, this is the transfer function that we get from this. We can of course get transfer functions from this one. So transfer function will be T I minus A minus B plus D. So this is a transfer function, and if D is there is no direct feed forward, then we say this is like strictly proper transfer function. That means number of poles is greater than number of zeros. And if D is non-zero, in that case there is this proper transfer function where number of poles is equal to number of zeros. So this is what we have seen, that in most of the transfer function that we have dealt with, their number of poles is greater than equal to 0, because that is a realizable transfer function. So this much we know how we are relating this transfer function with state space. Okay, then we saw that this A matrix, eigenvalue of this A matrix, so we can say SI minus A matrix basically, characteristic. So it's related to poles of the transfer function. Now that means if the eigenvectors of this A matrix are in negative, so that means poles of the transfer function are in left half plane, and we say that that this system is a stable one, and we say this is a Harvard matrix. A matrix is a Harvard matrix. So that was about the stability. Now we say that this is the system, this is a plant, x equal to plus du, y equal to cx plus du. So from there we know that how this system behaves and whether that system is stable or not. Now we want to have some change in the response of the system, and we want some other type of response, which is desired response. So we are including a controller which provides input to the plant, and This is based on some feedback from the plant. So this controller has to be designed such that desired performance is reached or achieved. So when we are dealing with transfer function, we said that okay, there is a reference which is being provided. So as of now, we'll just avoid this. We'll say that okay, the reference is set to 0 and we'll do the analysis. So if a reference is set to 0, that means this system should go to the state, should reach 0 with initial condition. Some initial condition with input applied, it should reach to 0. That means it is saying it's kind of a set point tracking problem or regulation problem. And this also leads to determination of whether system is stable or not. So for this, to do this, to design the controller, we need to know whether it is possible to shift the poles or not. Like for transfer function, we are seeing where for any design specification, we are saying that okay, the poles are here, so we have to shift poles such that the desired response is achieved. So we are seeing the root locus and we were shifting the pole somewhat. Suppose this is the new location of the pole. So according to this, we had some response. Earlier we had this kind of response. Now we have some fast response. And this is a desired response kind of thing. So what we are doing, we were shifting the pole or changing the location of pole. So that means we have to see if we can change the location of eigenvalue of the A matrix. Now this leads to the concept of controllability. Okay, so what we have seen in lecture that if this is a system and we want to see if the system is controllable or not. So if it is controllable, then only we can shift the pole from one location to another location. So we know the response of the system will be e to the power 80 x0 initial state plus e to the power a t minus tau v. So this is the response. Now for shifting, we can say xt minus e to the power at x0 is equal to we want that this change can be anywhere. I mean, from any initial location, it can be changed to any final location. From any state value, initial state value, it can be changed to any final state value in a finite time. So that means this should belong to Rn, this whole. And therefore, we can say that, okay, that this will lead to this controllability matrix. And we say that this leads to B. So let n minus 1b having a rank which is n. So that means this matrix will span the space of I to the power n. So its rank should be n in order to control this one. So that in that case, all the states are controllable. If any of the states are not controllable, then in that case, rank will not be equal to 1. It should be less than n. And in that case, rank of C, which is controllability matrix, which is less than n. So if uncontrollable poles controllable states which are not affected by input stable, then we say that system is stabilizable. But if uncontrollable poles are not stable, that means given any initial state, even if we control the, suppose we are trying to control the states and we have changed one state to here, another state should decay like this, which is not controllable. So it should go to 0. If it is stable, it would go to 0, x2 and x1. So this is x1, this is x2. But in case of this is not stable, so we are trying to, this x1 we are trying to track, and we are saying that okay, we control this and we are changing, this is how it will evolve given the input. But x2 will not be like this. X2 may go to very high value, may become unbounded, so that system becomes unstable. So that is not stabilizable. Okay, so overall thing of this like controllability and like concept of this controllability of the system is this one only. And we say that we verify a system is controllable or not by this way, that we see whether the rank of this controllability matrix is n or not. So rank is full rank. So in that case, what we say that if it is a full rank, that means this determinant of this matrix is not equal to 0. So we'll do some questions related to this. So suppose this is one system, x dot equal to lambda 1, 0, 0, 0, lambda 2, 3. X plus 0, v1, v2, v3, v. Okay, so this is a model form or diagonal form because these eigenvalues are around eigenvalues. And we have to see whether this means in what condition this system is controllable. So for this, what we have to do? We have to check whether this system is controllable or not. So we will just determine the controllability matrix. So this will be B, A, B, and A square B. So B is simply B1, B2, B3. And for AB, so we'll just multiply these two matrices, we'll get B1 lambda 1, B2 lambda 2, and B3 lambda 3. Okay, and then we have A square. So A square is simply lambda 1 square, lambda 2 square, lambda 3 square. And we again multiply this, we'll get B1 lambda 1 square, B2 lambda 2 square, B3 lambda 3 square. So this is the controllability matrix. Now for this to be of rank 3, because for controllability, this should have rank 3. And determinant of this should be, should not be 0. So we will try to find the determinant of this. So we just equate this. This one will be B1, B2 lambda 2 minus into B3 lambda 3 square minus B3 lambda 3 into B2 lambda 2 square minus B1 lambda 1, and then we have this B2 B3 lambda 3 square minus B3 B2 lambda 2 square. Then we have B1 lambda 1 square. This cross multiply these two. We have B2 B3 lambda minus B3 B2 lambda 2. Now we just simplify this one. That B1 B2 B3. Just take. If you see, we can take out here it is B2 B3. Here also we can take out B2 B3. Here also. Apart from this, we have lambda 3 minus lambda 2. 2 minus lambda 1. 3 minus lambda 1. So this is the determinant of this one, and this should not be equal to 0. So for this not to be equal to 0, what should be satisfied? This should not go to 0 because this is multiplication. All of these terms should not go to 0. That means B1, B2, B3 should not be equal to 0, and lambda 1 should not be equal to lambda 3 should not be equal to lambda 2, lambda 1 should not be equal to lambda 1, and lambda 3 should not be equal to lambda 1. Okay, so that means eigenvalues should be distinct. Should be lambda I should be distinct. This is one, and another is that this element in B matrix should not be 0. Where I belongs to 1, 2, 3 because there are 3 eigenvalues. Okay, so this is a condition for countability of this system. Let's see a system of another form, which is in Jordan canonical form. So we have x dot equal to lambda 1 and 0, 0, lambda 1, 0. 0, 0, lambda 1. X plus B. So this is C1, C2, C3. Okay, so this is a system. Again, we have to check whether this system is controllable or not. So if it is controllable, that means we can place or shift all the poles or eigenvalues of the A matrix. And if it is not controllable, that means we have to find which states are controllable, and if the uncontrollable states are stable, then we can say, okay, this system is stabilizable, and we can design a controller So for this one, again, we'll compute this matrix. This V, A, B, and A square B. Okay. So this would give C1, C2, C3, and then we have C1 lambda 1 plus C2, multiply with this one, and then we have C2 lambda 2 plus C3 and C3 lambda 1. This is lambda 1. Then we have A square B. So when we computed, this will be C1 lambda 1 square plus 2 C2 lambda 1 plus C3. Then we have C2 lambda 1 square plus 2 C3 lambda 1. And at last we have C3 lambda 1 square. So this is a controllability matrix. We find the determinant of this one. This would be minus C3 square. We solve this. So this should not be equal to 0 in order of the system to be controllable. Now in this case, the only condition is that C3 should not be equal to 0. Even if this C1, C2, all these are 0, it doesn't matter, but the C3 should not be equal to 0, and then this system is controllable. So we have now we'll deal with third form, standard form, which is the controllable canonical form, and we'll see what is the condition for this controllable canonical form. System in this controllable canonical form to be controllable. Okay, so we'll try to find controllability matrix for this one. 0, 0, 1, and then we'll have this 0, 1, A1, because this is multiplied to first column, this is multiplied to second column, this is the third, and summation of these. Then we have A square B, so we'll have 1, A1, A2 plus A1, A square. Okay. This is the determinant of C. These two terms we have this one, so we multiply, but this is multiplied by 0, so this goes to 0, this one also goes to 0, remaining is this one, 1. So if we find this minor matrix of this one, this is simply 0 into A1 minus 1. So this will go to minus 1. Now this is not equal to 0. So for this system, it doesn't depend, like this is the only condition that it is always controllable. Obviously, we have found out controllable canonical form. Until unless the system is controllable, we cannot determine this controllable canonical form. Okay. So of equal to 0, A1, 0, A2, 0, 0, 0 plus BU, where A1, A2 is not equal to 0. for this system where B is unknown. So B can be any matrix B1, B2, B3, which are unknown. So we have to find what should be number of non-zero elements. Find number of non-zero elements in B matrix of the system is controllable. Okay, let us determine this controllability matrix. Suppose that B1, B2, B3 are the elements of the matrix. So we have this. And B2, A1, this B3, A2, 0. Then we have a square, B3, A1, A2, 0, 0. Now, determinant of this should be non-zero. So if we find this with respect to this should go to 0, and then we have again this one. This should again go to 0. Remaining term is this one, so corresponding to this one. B3, A2 multiplied by B2 into 0 minus B3 square A2. What does this give? Yes, minus B3 cube A1 A2 whole square. Okay, so for this should not be equal to 0. So we know that A1 and A2 are not 0. It is given. So what does this mean? Just B3 should not be equal to 0. So the condition is B3 should not be equal to 0 for controllability. So the number of non-zero elements in B matrix for system to be controllable should be what? It can be up to 3 maximum. But the thing is minimum this B3 should not be 0. So we can have B1, B2 equal to 0. In B3 we can have non-zero. So minimum number of element is say that minimum number of non-zero elements which is equal to now based on earlier question. We have this. We have the system 0, 1, 0, 0, 0, 1, A3, A2, A1, X and Y equal to 0, 0, 1, X. So it is asked condition for observability. Okay, so regarding this observability, so when we were saying that dealing with this slide, we said that okay, this is the plant and we are trying to design the controller. So we have some state feedback and we design the controller so that we give the feedback multiplied by some gain so that the eigenvalues of this A matrix are shifted to desired location. Now in that case, we are assuming that all the states are available. So then only we can design the controller. Now it is not necessary that all the states, because these are internal variables. So some, like, it may be possible that if values are available, it may also be possible that the values are not available. So what is available to us is the output. We have this AX, this is X matrix, this is X dot, and we have this AX plus 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 VU, and then we have P here, saying that this is the Y. If Y is equal to C, if that is D is equal to 0. And then we have this U, which is coming from some controller. So suppose this is the controller. This is simply a state feedback. So there is again K, which is multiplied with this X, and this is the output. So this is the controller. We have output, but what we have from sensor is the output. It's not the state. So in the transfer function, when we are dealing, we're seeing that Y by R. In that case, we have to utilize this one. This is the available from sensor. And to design this controller, we need to estimate this state from this output. So we have some estimator. It gives X cap, and some property has to be satisfied so that this overall system works fine. So in that case, this loop is not available, this one. And this estimator should be such that this X cap and X should converge. It's not like this is going from, like suppose this is evolving from initial state to here like this, and this estimator same initial state, it is evolving like that. So there is some error. However, we are trying that these two should converge as time with time. So there should be some converging property like that. So in that case, in order to design this estimator, we want that from output and the given input. We can say from measurements and input data, and we determine the state. So if this is possible, we can say that system is observable. We come to the concept of observability. Okay. So for This one we have the like we have seen y equal to c, the at xpo tau d tau is a t. This is yt. So yt is basically equal to c into x because this is the response of a state. Now we have seen in lecture this number of states may be greater than or equal to output. So if it is equal to, then we say, okay, we have suppose C is x belong to r to the power 3 and we have C is equal to 1, 1, 1 along the diagonal. In that case, what is y? Y is equal to x is C into x and this is simply x1, x2, x3 which belongs to r to the power 3 again. So in that case, if this is a square matrix, we have this state, we can find the output. If we have this measurement and we have this P matrix, we can find the state. So this is simply the C inverse Y. But in general cases, the number of states are greater than number of output. And in that case, we have to collect this Y matrix, number of observation Y1, Y2, say Yn, kind of this. And we have to relate this and we come to the condition of observability matrix, which is C, CA, CA square, CA to the power n minus 1. And the rank of this matrix would be n. Okay. And we have also seen that if we have a system x dot equal to ax plus bu, y equal to cx, then we can find a dual system. We have this dual system which is z dot equal to a transpose z plus b transpose u and y equal to that is b into z. Okay, I'm not confident about this clear vision, but this is the overall thing. These are the dual systems. So in this case, if we say that A and B, this pair is observable, or sorry, controllable, then in that case, this one is observable. So we will just apply this duality concept, dual system concept to this system. This is a system. We have A is like this and B is this. So we have to find whether this is a C and this is a A matrix. So we are saying that this system is observable. So that means if this system is observable, we want to find, then we can say the system which is the dual system of this one should be controllable. So in this case, what would be dual system? Dual system will be 0, 1, 0, 0, 0, 1, A3, A2, A1. This is C, the C transpose. We have C transpose which is 0, 0, 1. So for that system to be observable, this one, we want this system to be controllable. Now for this system, this is a controllable canonical form. And for this system to be controllable, we have seen the condition. It was that it just said whatever the value of A, B, this is always controllable. When this is the form. So that means this system is always controllable and therefore this system is observable. Observable. This is the next system. So we have this system equal to AX, Y equal to C1, C2, C3, S. Now it says that what is the condition for observability of this system? So for this system to be observable, the dual should be controllable. So dual means if this is A, then A transpose, if this is C, then C transpose. So A transpose, C transpose should be controllable. Let us see what is A transpose. A transpose is simply this one only because this is a diagonal matrix. And C transpose is C1, C2, C3. Now this is a diagonal form and these are the elements of the C transpose. So from the first question that we had done, we can say in the what condition this system is controllable. So this is the question. We have A matrix, we have this B matrix, and we said that for this to be controllable, these elements of B matrix should be non-zero and all the eigenvalues should be distinct. So here all the eigenvalues 7, 4, 1 are distinct. And the C1, C2, C3 should be non-zero, equal to 0. So this is the condition for observability of the given system. Okay. So this again we can verify. This is one way using duality. Another way is that we construct the observability matrix for this system. So this will be C1, C2, C3, C, CA, CA square. And then we will do 7C1 plus C2, 4C3, so 49C1, C2, 16C3. Okay, so determinant of this matrix should not be 0 in order to be observable. We just find the determinant of this one and we get 54, C1, C2, C3 not equal to 0. So for this whole term to be not equal to 0, all the individual terms should not be equal to 0. This implies C1 is not equal to 0, C2 not equal to 0, and C3 also not 0. Okay. So any of the approach you can apply and get to same result. Fine. So now we have gone through the questions related to controllability and observability concepts. So you know how to verify whether system is controllable and observable, and why it is required to see observability and check observability and controllability of the system. So we'll now proceed to this controller design problem. We can say pole placement problem, or also we can say state feedback controller design problem. So we have this question. We have the system x dot equal to ax plus bu, and a is 1 minus 2 0 0 1 2 1 0 1, and b is 1 0 1. Okay, and we have to find k having k1, k2, k3 as elements, so that if we have this input is equal to minus kx, then the closed loop poles are at minus 5, minus 3, and minus 1. Okay. So we'll use this Ackermann method. We'll find the characteristic polynomial of the system with desired poles. The poles are it minus 5, minus 3, minus 1. So we have s plus 5, plus 3, and we have plus 1. To simplify this, we get s cube plus 9 s square plus 23s plus 15. Now this phi of a, this is non-zero because this is a characteristic polynomial of closed loop system, and this is our open loop system which has this matrix A. It will simply be a cube plus 9a square plus 23a plus 15. Then we'll just solve this. So we'll be doing the whole calculation. I'll write the values 44, 24, So this is the matrix. After that, what we have to do? We have to find this controllability matrix. So we have B, AB, and A square B, because we know this value of A and B. So this controllability matrix we can find out. Let's do 1. Now just we have to include this in the formula of K. So from Ackermann's formula we know K is 0, 0, 1. The proof is there in the lecture, so you can go through that if you have any doubt in proof. This is y of A. Now once we multiply all this, we will get 16. Minus 16 and minus 4. For this one, the closed loop system has 4 sides, minus 5, minus 3, minus 1. Okay, this is one way. This is the Ackermann method. And then another way is that we just transform the system in a controllable canonical form and try to find out what is the K matrix. So let us suppose the same system and we have to find the matrix A, so that is equal to minus K places a closed loop pole. At minus 6, minus 4 and minus 2 for the same system. So now this time we'll try to find the controllable canonical form and then we'll try to find the scale K for the state feedback. So what is the determinant of Si minus A? This is the characteristic polynomial with determinant of Si minus A. And from that system, for this system, we find this A mm, 0. Okay. From there, we'll get S cube minus 3S squared plus 3S plus 3. Right. So from there, we know how can we convert this system? We have to find some similarity transform. So we have seen that if there is a system x not equal to ax plus bu, and if we transform this state into using some transform, So suppose we have a state vector which is x cap is equal to P inverse x. Okay. Or here we can also say x is equal to T x cap. So now we can write this system in terms of new state which is x cap. So this is T x cap dot equal to A T x cap plus B U. Then this will lead to x cap dot equal to T inverse A T x cap plus T inverse B U. Now we have this system and it has to be converted to controllable canonical form. So we have to find this transform T. Such that we can have this form of the system, and for both the systems the eigenvalues are same, so we can do this. And for this system, whatever the value of k is, so suppose for this system we get a value of k, so you will apply u equal to minus k f cap. Now for this system, original system, what would be the value of k? This will be minus k x cap is P inverse x. So this would be the value of k for original system. K P inverse. Okay, so we have to find this T matrix. So for that, there is this procedure. So we have this characteristic equation, and from there we will calculate a matrix. So suppose this is the characteristic equation, which is s cube plus b1 s square plus b2 s plus b3. Then we have this matrix W, which is b2 b1 1 1 1. We'll just find this matrix. So for our case, for this one, this is x cube minus 3s square plus 3s plus 3. That means for this case, b1 is equal to minus 3, b2 is equal to 3, and b3 is equal to 3. So we'll just replace this 3 minus 3 minus 3, 1, 1, 1. Okay. Now to find that matrix, what we do, we just multiply this controllability matrix with this W. B, AB, A square B, and we have W. So overall, what we get, zero, zero, minus 3, minus 1, minus 2, minus 2, 1, 0, and 1. Okay. So this is the T matrix. Now what we have to do, we have to find a new A matrix. The new A matrix will be T inverse AT, and new B matrix will be T inverse B. So A cap is equal to T inverse A T. So just multiply this, 3 multiply and cross multiply by this, we will get 0, 1, 0, 0, 0, 1, minus 3, minus 3, 3. Similarly for B cap, which is T inverse B, we get 0, 0, 1. So this is in controllable canonical form. So what is the value of k? So for this system, a cat minus b k cat. This is overall closed loop system matrix. I will just have this. So this should lead to 0 1 0 0 0 1 minus 3 minus 3 3 minus 0 0 1 1 k1 k2 k3. This multiplies this, we will get a cat minus b k cat b cat k is equal to 0 0 minus 3 minus k1 1 0 minus 3 minus k2 0 1 3 minus k3. Okay. So for this matrix, this is a closed loop matrix. The characteristic equation will be determinant of Si minus A cat plus B cat K. If we find the determinant of this one, this would give S cube minus 3 minus K3 S squared minus 3 minus K2S minus. Oh, so this is a characteristic equation of this closed loop system, and we know from the pole placement that the characteristic equation should be such that it should have closed loop poles at this point, these values. So the desired one is S plus 6, S plus 4, and we have S plus 2. Now if we expand this, we get S squared S cube plus 12 S squared plus 44S plus 48. Okay. So this is closed loop characteristic equation. This is the desired one. So that means the value of k should be such that these two should be equal. So we can now equate the coefficients. So 3 minus k3 should be 12. 3 minus k2 should be 44. Minus 3 minus k1 should be 48. So if we equate this, what we get? This k is equal to 45, 41, and 15. Now this k is for transform system. For the given system, which is not its controllable canonical form, which is this one. What we need to do, we need to find the k, and this k original should be, we have seen for this one, this would be k t inverse. This will be equal to k t inverse. T matrix we have found out, this is this one. So once we do this, we get 30 minus 20.5 and 15. Okay. So using this value of K with actual system in state feedback, we are able to trace the force of the closed loop system to -6, -4, and -2. So this is another procedure or approach for designing the state feedback controller. The earlier one was this FMS method. Now let us proceed to next question. So now we'll see the design of controller and observer. So for this question, this Ackermann's method based and all, this is state feedback, where we can see this input is U equal to minus K into X. So input is you can say minus K1 X1 minus K2 X2 minus K3 X3. So it requires knowledge of X1, X2 and X3, all the states of the system. Now we have seen why observability is required for a system to be observable, so that because the measured quantity is output. It's not it may not be all the states. So these states has to be estimated based on the output. So in that case, observer has to be designed. So we'll see this one. How do we design the observer and state? So the question is, we have the system x not equal to ax plus bu. And now y is not equal to x, it is y equal to cx, where c is 1, 0, 0, and a is 1, 1, 1, minus 1, 0, 1. This is 2 minus 1, 3, and b is 1, 2, and 1. Okay, so we have to design a gain, state feedback gain. So that if input is u minus kx, then a minus bk, which is a closed loop system, it has poles at -2, -1, plus minus j. And since the output is just x1, x2 and x3 are not measurable, we try to estimate x by x hat. X hat is estimated value of x using full order observer. So all the states are being observed. And for this observer, the poles are with poles at -4, -5, -3. Okay. So that means we have output as feedback. We have this plant Y, and there is this state X. So we have again a model of this plant, which is X cap equal to X plus BU, and we have some term additional, which is L Y minus Y cap. So Y is the input to the system, and from here we get X cap. We have this K minus K, and this is the input to this system. Gives us X hat. Now for this system, we have seen that the closed loop dynamics is X dot and E dot, where E is X minus X cap. In this case, this E dot should tend to 0, so that this X and X cap converges. This is A minus PK. This is the state feedback design. 0 A minus L. This is for observer design. X and E. So for this overall system, what is the total number of state variables? It is number of states for X and number of states for E. So this is of X, there are 3 states. So for E also there are 3. So total number of states is equal to 3 plus 3 is equal to 6. Okay. Now we have to design this K and L. Like we have to find the value of K and L such that the closed loop poles satisfy given criteria that this should lie at this points and these points. So for that, we can again do the same thing for earlier that we have done. Either we can convert this AB into this controllable canonical form, and then we try to find the transform and equate the characteristic equation, or we can use the Ackermann's method for this poles. And for observer with design, since we have A and C, so we'll try to do this for A transpose, C transpose, in pole placement for A transpose, C transpose. Again, for this one, either we can use Ackermann's formula or we can do the controllable canonical transformation. We just find out this one. We'll just use this. So earlier in the earlier examples, we have done the calculations. Now we are using this. For this part, we'll just use MATLAB. See if we can do this. Then we can directly use command. This command. Which requires the system matrices and the pole location. And this gives us the gain, state feedback gain. So for this question, what is the A matrix? This is this one. So we have A matrix, which is 1 minus 1 0. And then we have 1 0 minus 1 1 1 3. Then we have B matrix, which is equal to 1 2 and 1. We have C matrix also, which is 1 0 0. So we have to find the state feedback gain. So that will be A comma B comma, what are the pole location? Closure B. B. Minus 2 minus 1 plus I. Minus 2 minus 1 plus J. Minus 1 minus J. Okay. So this is the K matrix. 2.75. And 0.35 and 5.986. Now we have to find L. So we'll apply the same equation for controllability for the dual system, which is A transpose C transpose. And from there we'll get L transpose, and we'll just find the transpose of this one to get L. New one will be, this is A, this will be A transpose, and then this is C transpose, and we have 4 set minus 4 is minus 5 minus 4 and minus 3. So this is K. So what would be L? L will be K. Now 60 minus 90. Okay, it seems I have taken wrong system. So A is this one, but in this A we have 1 minus 3 equal to 2. And this is the system. This is the K matrix, and for L1 we find this one. So for L we can get K cap. This is like this. So what is the value of K? One point 1.18, 0.32, and 5.5. And for L, we have 16, 0.9, and 46.5 centimeters. Okay, so we have found out KNS, and when we apply this gain, then system is having pole in left half plane, that means it's stable and it's controllable, so it will have performance corresponding to these poles, and for observers these are the closed loop poles. Okay, so I think we can stop now. We have solved enough questions. So are there any doubts? Okay, so we'll stop here.